Hey guys, sorry I haven't been here. I'm hoping to be back tomorrow, but for today you're gonna have to write a lot because this is all like a lot of writing in this lesson. The first thing I want to go over is the 10% condition. It's also sometimes called the rule of thumb. So you can copy this into your notebook. When taking a random sample size n from a population of size capital N, we can use a binomial distribution to model the count of successes as long as n is less than 0.10 of the population. Okay, so what that means is if the independence isn't met by the normal ways, this is actually a way to show independence. So basically, as long as your sample size is big enough, each trial doesn't really have to be independent. We consider it to be independent if this 10% condition is met. It's also sometimes called a rule of thumb. So you want the population to be at least 10 times the sample size. So that is something that you have to know. And when I come back, I'll go over all of this again, but I wanted you guys to see all of this today. All right, so there is a lot of notes on here. So, while you're watching the video, you can pause it so that you can copy them all. But I'm also going to talk through them to make sure you understand them. So you're going to copy all this into your notebook, but geometric random variables is pretty much the last thing in this unit that we have to cover. So a geometric random variable is a discrete random variable that counts the number of trials required to obtain the first success. So basically that's always on the last trial is when you'll get your first success. So if it happens on the first try, great. But, if it could happen later. So, for example, if you're rolling a die and you're looking for a 6, you roll it as many times as you have to until you get a 6. And the probability of it being on the first roll or the second roll or the third roll is a calculation that we're going to do. So the properties of them, so you know the difference between this and a binomial random variable. There is no fixed number of trials because it's just whenever the success happens. So in a binomial, there is a number of fixed trials. We'll say if you roll the die 12 times, how many 6s or whatever. But this is saying, when are you going to get the first 6? How many tries is it going to take? So that's the difference there. The rest of the conditions are the same as binomial. So all trials must be identical and independent. Each trial has exactly 2 outcomes, success or failure. The probability of success is called P and failure is 1 minus P. So all of that is the same as binomial. The only one that's different is there's no fixed number of trials. Okay, so the probability distribution looks like what I wrote there. So x is 1, so probability is just P. When you get to 2, it's P times 1 minus P, and then when you get to 3, it's P times 1 minus P squared. 4 is P times 1 minus P cubed, and it keeps going. The formula for it is given. The independence condition is met if the population is at least 10 times the sample size. And that's what I just talked about at the top, that 10% rule. All right, so in geometric probability distributions, x represents the number of trials it's going to take in order to obtain the first success. So the formula for geometric probability, if you have to write it out, is the probability of x equaling n is P, which will be in the problem, that's the probability of success on one trial, times 1 minus P to the n minus 1. That formula is given on your formula sheet for the AP. This is given. So, you don't have to memorize it, but you have to know when to use it. So you have to know when it's geometric or binomial because they're different with their formulas and they're different to do on the calculator. So I'm going to show you how to do that as well. So here's our first example. And I know I'm going fast, but you can pause the video to take time to write the notes. Consider a geometric random variable x with a p of 0.25. The first question is P x equals 3. That means what's the probability that the first success occurs on the third try? That's what x equals 3 means in geometric. So what I plugged in there comes right from the formula, which is given on your formula sheet. So we want the probability of x equaling 3. So you plug in the probability of success on one try. which was given. And then this is 1 minus that. And then the exponent is always 1 less than n. And you just put that in your calculator. So if you just type it in as 0.25 times 0.75 squared, you'll get 0.140625. But if you do want to do it with the menu, it's second vars F. The easiest way to get there is press second vars and then arrow up, and you'll get to F. Geomet PDF means to do one value. And we were just doing the value of x equals 3. That's why we did PDF. But this is how you do it with the formula. All right, the second example, we're still using the same probability of 0.25. But now I want the probability that it occurs in less than or equal to 2 tries. So that means either 1 try or 2 tries. So you can use second vars G, which is geometric CDF, because now we're talking about cumulative from the bottom. So less than 2. Now this time 0 is not included. It's just 1 or 2. 1 is the lowest x can be for geometric. So there is no 0 there like there is for binomial because it's different. For binomial, you're doing something a certain number of trials and you could get 0 successes. But for this, you're going for that. It has to be a success. It has to be either 1 or more because you're looking for the first success. So it can't ever be 0. So when you do geometric CDF, you can do it on the calculator. If you did this with the formula, you'd have to plug in 1 and 2 and then add them together. Now, greater than or equal to 4 is a pain because it's greater than, and your calculator will only do cumulative from the bottom, just like with binom. So greater than or equal to 4, you'd have to do 4, 5, 6, and it would go on to infinity. So you can't actually add those all together. So you have to do the 1 minus. And since we're including 4, 5, 6, we're not including 1, 2, and 3. So you do 1 minus, it's still CDF there. 1 minus the probability that x is less than or equal to 3. So when you do geometric CDF, the p is 0.25, and then the x value you would put 3 because you're talking about it not being 1, 2, or 3, and then you have to do 1 minus. Okay, the means and expected values and standard deviation for this are also given formulas. You don't have to memorize any of these formulas. You just have to know when and how to use them. They're all in the formula sheet. So the mu of x for this is 1 over p, and the standard deviation is square root of 1 minus p over p. Geometric distributions are always skewed right because the more trials, the closer to 0 the probability gets. So we never use normal approximation for these because they're not normally distributed the way binomials can be. So I know that's a lot of information, but hopefully you understood it. I'm going to go over it again when I come back. All right, so here's an example that came from your old textbook, but I'm going to use it anyway because I couldn't find one like it in the new textbook, and I liked it. So it's about a Major League Baseball player, and his average was 325. That means that that's how often he gets a hit when he comes up at bat. He wants to calculate the probability that he'll get his first hit in the new season at his first at-bat, which is pretty hard to do. You define a success as getting a hit, and the random variables x is the number of at-bats. So the probability that he'll get his first hit on his first at-bat is x equaling 1. So p is 0.325, and then you plug into the formula, or you can use geometric PDF to get that answer as well. But, if you have to show the formula, it's 0.325 times 0.675 to the 0, which is 0.325. Which makes sense. If that's his average, then him getting it on the first at bat has that same chance, 0.325. Okay, then the next one's asking, what's the probability that he'll get at most 3 at bats before he gets his first hit? So at most 3 means he's getting either 1, 2, or 3 at bats. So that's a geometric CDF from 3 down, which is 1, 2, and 3. So you can do that on the calculator with second vars G. Then the next one's asking the probability that it's going to take him more than 4. More than 4 doesn't even include 4. It includes 5, 6, 7, or more. So you do 1 minus the probability that it's less than or equal to 4 with geometric CDF again. And then D asks about his expected number of at-bats. Well, expected value is the mean. So you use the formula, which is given. It's 1 over P. And it comes out to a decimal, but at-bats are whole numbers, so you round it because it makes sense that it'll be about 3 at-bats. If you left it as 3.0769, that would be okay, but, you don't have decimal numbers of at-bats, so it makes sense to just leave it at 3. Now, they didn't ask about the standard deviation, but I wanted you to use the formula once, so I put it there. Standard deviation for this example, you use the square root of 1 minus P over P, put it in the calculator. Very easy, 2.528. So I know that was kind of a lot of writing and I talked fast, but you can always pause the video so that you make sure you wrote everything down. I am going to have you post your notes so that I see that you did it. And your homework is right here, page 459, 110, 112, and then 113 to 115. Also, we're going to have a test on Tuesday next week on this whole chapter. But we have plenty of time to make sure we know everything by then. All right, hopefully I'll be in tomorrow.